Okay, I think my screen is now visible. Okay, so let us start with the random variable. So is my screen visible?
Yes, sir.
Okay, okay,
Yes, sir.
okay. So we have an experiment and a sample space and a sigma field, which you can take as the power set. Rule, kindly mute yourself. Rule x, which assigns a real value x omega to each omega element which is in the sample space is called a random variable. So which is a rule which is basically takes the value of sample space and convert into a real value. That is, x is a function whose domain is sample space omega of outcomes omega small omega, which belongs to capital omega, and whose range is some subset of the real numbers. Okay, so let us take an example. So let us toss the coin 2 times, then sample space is HH, HT, TH, TT. So this we let us say that we denote this by omega 1, omega 2, omega 3, omega 4. These are the basically elements. These are basically same. So here you can take f as power set. So let we define the random variable as which is counting number of heads. So if we apply x on omega 1, we will get 2. If we apply over omega 2, we will get 1. Similarly, and x omega 4 is 0. Okay, so similarly, we can take some event also, which is nothing but some element from the f. Okay, so this we can take as omega 2, omega 3. So correspondingly, we can take some element from the range space, which is a real number or subset of real. So that we can take as 1, because this is x is when applied, this is your omega, and this is a, x is applied here. So this is basically I. When we take this as omega, this as a as this. So now when this is applied, then this becomes x omega. Okay, so I here becomes omega 2 comma omega 3. X is counting number of heads. This is 1. Similarly, a2 we can take, which is, let us say, omega 2 comma omega 3 comma omega 4. If we want to write in terms of range, then that this becomes, x is counting number of heads. So omega 2 number of heads is 1, and omega 3 1, omega 4 as 0. So 0 comma 1. Okay, so for each event, A, probability of A, which is probability of omega such that x omega belongs to I, which we can take as Pxi. Okay, so here A and I are equivalent events. A and I are equivalent event. So if we want to find probability of I, we can find probability of A also. Okay, so using this, we can see easily that this assignment is meaningful if
Excuse me, sir.
omega, yes,
So what does I represent here?
I is some event in the, basically you can say in the real line. For example, in this case, this is 1 only. This is some interval here or some subsets here of the real line. So,
Okay, sir.
okay, so here you can see that omega f and p is the probability model. Here r and corresponding sigma field and corresponding probability is there, px. Okay, so probability of A is same as that of probability px, because here probability is px, because here sample space is different, which is r, pxi. So we are saying that A and I are equivalent event. If we find probability of A and pxi, both will give us the same answer. Okay, so what is the then random variable x? So this is reasonable to insist that each interval on R to be assigned probability consistent with the assignment P of to the event omega. Assignment I, which is subset of R, is meaning this probability P omega such that x omega belongs to I is meaningful if omega x omega belongs to I are events. So therefore belongs to I should be event. So then it is meaningful. Then x is said to be random variable if this happens. This is equivalent to saying that we can show that this is meaning that omega such that x omega, okay, this basically less than equal to x, okay, belongs to f. That is meaning same that of x inverse minus infinity to x is an event. That means this value should be an event, then X is a random variable. Okay, so now let us toss a coin. Okay, so let us say that we toss a coin, we will get head and tail. And X is the counts the number of heads. Then we can take the F as power set phi h t omega. Then what is, if we apply X on H, we will get 1. If you apply X on T, we will get 0. So what is omega such that X omega is less than equal to X, which is nothing but this value. So if we take, because you know that if we have T and H, then correspondingly we will have, if we apply X, 0 and 1. So when X is less than 0, then corresponding value of omega is nothing, phi. From here you can see when X is between 0 to 1, it will include 0 only in this case. It will contain only T. When X is greater than equal to 1, this will include previous case also, 0 and 1. So therefore it will contain H and T both, that is omega. But you know that this all three values belongs to F, event. So therefore this is an event, therefore X is a random variable. Okay, in this fashion you can see that X is a random variable here. Okay, so in this case you can see that when R is the real line, then corresponding subintervals contains, this is containing subintervals of real line. Okay, this B, and this is known as the Borel sigma field. Okay, so now let us define what is first of all, let us define what is a distribution function. Let us first of all define what is a cumulative distribution function, CDF. Or distribution function. So probability model is omega, F and P. This is the probability model. So for event X, which is less than equal to small x, we define Fx, or you can write Fx also, one is the same thing, or small Fx also. So this is probability X is less than equal to X. This meaning is that probability omega such that X omega is less than equal to x. Okay, where this x belongs to R. That means, okay, so if we want to write in terms of Px, this will be Px minus infinity to x. Okay, so
capital X is some event here, or is it a random variable?
capital X is a random variable here, and x is less than equal to x is an event, which is nothing but this value. Just a notation. Omega such that x omega less than equal to x. Okay, and this Px is here. This Px is here. Okay? Because events are equivalent basically, so their probabilities will be equal. Because here you have seen that some interval of real line will be there or sub intervals of real line will be there. So therefore, this is minus infinity to x. Okay, so let us take some example of cumulative distribution function. Okay, so let us first of all omega as HH, HT, TH, TT. Okay, so X is counting number of heads. So X you can take as 0, 1, 2. So corresponding probability X is equal to X. So this is number of variable case X is equal to 0. Number of heads is 0, 1 by 4. This is 1 by 2. This is 1 by 4 because you know that when X is equal to 0, then number of heads is 0, 1 by 4. Similarly, 2 by 4 when X is equal to 1. TH, HT, TH. Okay, corresponding we can take as power set, and corresponding range space is 0, 1, 2, which is containing these points. So what is the CDF here? This is known as the, because this is a discrete type random variable corresponding, this is known as the probability mass function, PMF, probability mass function. And what is the corresponding CDF, cumulative distribution function? So this is nothing but probability x is less than equal to small x. This is nothing but sum of the probabilities which are below x, which are below the point x. So when x is less than 0, corresponding probabilities are 0. When x is greater than 0, less than 1, for any value of x, because we have to define for each value of x. For any value of x between 0, which is greater than equal to 0, less than 1, only this point will be there. This point will not be included because 1 is not there. So 1 by 4. When x is greater than equal to 0, greater than equal to 1, less than 2, this will contain, because all the probabilities we have to sum below that. So this will be summation of both these. That will be 1 by 4 plus 2 by 4. That will be 3 by 4. And when x is greater than equal to 2, this will be sum of all the probabilities here, because only maximum point is 2 here in this case, discrete case. So therefore this is 1 by 4 plus 1 by 2 plus 1 by 4, that is 1. Okay, so this is the CDF here. Okay, so in this fashion, we can have X and Fx. So this is, let us say, 0, 1, 2. So correspondingly, we will get 1/4 when X is between 0 to 1, value is this. When X is between 1 to 2, value is 3/4. When X is greater than equal to 2, this is this value. So in this fashion, this is the CDF. So you can see that in discrete type, because correspondingly, because only some points are there, 0, 1, 2, 3, and discrete points are there, or when there are continuous, when there are countable number of points, then we will get step function kind of CDF. Okay, CDF is basically this kind of, some steps are there like this. Okay, so therefore corresponding random variable is discrete type random variable. Okay, so now let us take another example of finding. This is the CDF. Let us take another example. So here it is clearly discrete type random variable X. A cathode ray tube is aged to failure. Omega is T such that T is greater than equal to 0, which is 0 to infinity. X is the life of cathode ray tube till failure. So Fx in this case is X is less than 0 and 1 minus e raised to power minus lambda x, where X is greater than equal to 0. Lambda is positive. So we can X Fx. So if we plot this, we will get this kind of CDF. Okay, so here you can see that this is continuous type. Okay, so also derivative also exists except some points. Okay, so therefore this is the CDF. We can also find probability density function here. As we have probability mass function in discrete case, this is the continuous case. Probability density function. So we can take the derivative of the CDF. We will get PDF. Okay, so what are the properties of CDF which we can observe from here? First is that CDF is between 0 to 1 for all X. You can see here and here also. Okay, also it is non-decreasing. in X. That is, X1 is less than X2. Fx X1 is less than Fx X2. Third is Fx is right continuous. Because you can see in this case it is continuous, but in the discrete case, when you are coming from the right side, you will get value. When you are coming from the left side, you may not get the value at certain points. Okay. For example, in 0, 1, 2. Okay, so that is f x x plus, where small x is basically point. So this is f x x. So f x x plus is limit as delta goes to 0, f x x plus delta, which is f x x. Fourth is limit x goes to infinity, value is 1, and limit x goes to minus infinity, fx is 0. For example, when you are going toward minus infinity, you will get 0 value. When you are going towards plus infinity, you will get 1 value. Okay, so these are some properties of the CDF. Also, fx f of a is basically can be written as, okay, we can write down probability of x is equal to a as f x a minus fx a minus, just below a, because this can be written as probability x is less than equal to a minus probability x is less than a. So that is just below a. So fx a minus fx a minus. So let x be a random variable, denote x, random variable x denote the number of defects in a device having CDF as x is less than 0, 0, x is greater than equal to 0, half, x is greater than equal to 1, 1. So find probability x is equal to 1. That will be f of 1 minus f of 1 minus. So f of 1 is 1, f of 1 minus just below 1, value is half. This is half. X is equal to 0. So this will be f of 0, half, f of 0 minus just below 0, 0. This is also half. Let us find out what is the probability that x is greater than 0, less than equal to 3 by 2. This is probability x is less than equal to 3 by 2 minus probability x is less than equal to 0. You can just easily see that this is 0. This is 3 by 2. Open here, close here. So this will be x is less than equal to 3 by 2 minus x is less than equal to 0. Close. Then we will get open 0 to close 3 by 2. So therefore this will be f of 3 by 2 minus f of 0. F of 3 by 2. This is 1 minus f of 0. Just can anyone tell what is f of 0 here?
1 by 2.
1 by 2. Okay, so 1 by 2. So therefore this value is 1 by 2. But if we want to find out this probability, x is greater than equal to 0, less than 3 by 2. So that will be probability x is less than equal to 3 by 2 minus probability x is less than 0.
That will be 0.
Yeah, so that will be 0 minus f of 0 minus that will be 0, because you can easily see that this will be closed here, that will be this minus closed this and open this. That means f of 3 by 2 minus f of 0 minus, but 0 minus just below 0 value is 0. So 1 minus 0, this is 1. So in this fashion, you can find out the answers here. Now, as we have seen that corresponding to CDF, we can have, if CDF is
Excuse me, sir.
step, yes.
So in the last step of that problem, how did you replace P of x less than 3 by 2 by f of 3 by 2?
This is the definition, na? Because what is the definition of the CDF? Definition of CDF is f x x is probability that x is less than equal to small x. But this CDF is given to us. So,
Okay, sir. Okay, sir.
so just replacing that function by f of this. Now we have seen that if we have the CDF as having jumps, then that is right continuous step function. Then corresponding random variable is discrete type, and we will have correspondingly probability mass functions. So for the discrete type random variable, we can associate a number px to each outcome x in the range space x, such that px is greater than equal to 0 and less than equal to less than 1, such that their sum is 1. The pair x px is called probability distribution and px is called the probability mass function. So as just we have seen that thing. So in, for example, this example, but if we toss the coin 3 times, we will get the sample space as omega is this, and HHT, HHT, HTH, THH, where head and tails, H and T are denoting head and tail, and X denotes the number of heads, tossing coin 3 times. So range space is 0, 1, 2, 3. Corresponding probability distribution or probability is when X is 0, this is number of heads is 0, 1 by 8. When X is 1, probability X is equal to 1 is 3 by 8. Similarly, x is equal to 3 by 8, x is equal to 3 is 1 by 8. So this is the this is also known as probability mass function, and this is known as the probability distribution. X comma px is known as the probability distribution. Similarly, we have continuous type random variable where we will have, if we have the corresponding CDF as continuous type, except some points we will have the derivative, so we can have corresponding probability density function. So x is the continuous type random variable. If we can associate a function called probability density function such that this is positive for all x and integration of this is 1, because here continuous type is there, so we have to, instead of summation, we should have integration. And if you want to find the probability x is between a to b, then because this function is there, okay, so some function is there. So if you want to find out the probability of that, we have to find, this is the PDF. So we have to find over this area basically. So that is basically integration a to b fx dx, where small f is the probability density function. Okay. And if you want to write in this in terms of CDF, this will be probability x is less than equal to b minus probability x is less than equal to a. Okay, basically less than a. Okay, but in the case of discrete, in the case of continuous type random variable, you can easily see that because it is continuous, so probability x is less than equal to a, probability x is less than a. Okay, these are both same basically. So therefore this is f of b minus f of a in continuous case. Okay, so therefore in this fashion you can write down this. Okay, so we can write down in this in terms of integration a to b fx dx, where fx is the probability density function. So x is the time of failure of an electronic device that has the following PDF. Now find out probability x is between a to b. So this is integration a to b, because a and a is greater than 0. So therefore into fx dx. Therefore this will be a to b lambda e raised to power minus lambda x dx. That is this answer. Then electronic device has left more than 10 days but less than 30 days. Is the probability x is greater than 10, less than 30, which is e raised to power minus 10 lambda by e raised to power minus 30 lambda. Okay, except this, we may also have which is known as the mixed type random variable also. What is mixed type? Basically, which is the, because in discrete we have step function, CDF has step functions, and in continuous type we have continuous type. So, but when we have mixture of both of them, that means let us say that this value and this value. So, okay, so then we can have okay corresponding CDF is, let us say this, okay, which is a mixture of both of them. So, so therefore we can write down this is a mixed type random variable. So for example, we can have, let x be the life time of an instrument which may fail immediately on installation with the probability 1 minus p, or it may live up to age x with probability p into 1 minus e raised to power minus lambda x, x is greater than 0, lambda positive. Then fx, when x is, this is probability x is less than equal to x. This is when x is less than 0, this is 0. When x is greater than equal to 0, this is 1 minus p plus p 1 minus e raised to power minus lambda x. Okay, so this is a step function basically, a mixture of step function as well as continuous. So therefore, this is a mixed type random variable. So this is a mixed type random variable. X is random variable here. Now let us start with the any question till now. Now let us start with the expectation. So expectation of x, for example, we have discrete type random variable. Then, for example, we have, let us say, some points. Okay. 1, 2, 3, 4. Okay. Then what is their average? 1 plus 2 plus 3 plus 4 by 4. If we give them equal weightage, that is 1 into 1 by 4, 2 into 1 by 4, 3 into 1 by 4, plus 4 into 1 by 4. Okay. So therefore, if we give equal weightage of them, we will get this value. Now, if we give different probabilities such that their sum is 1, because this is 1 by 4, 1 by 4, 1 by 4, 1 by 4 is 1. Okay. So then we may have this thing 1 into P1, 2 into P2. What is the corresponding probability of into P3? 4 into P4, such that sum of Pi is 1. Okay. So this is the basically we can denote as expectation or the mean value. Okay. So therefore, the expected value of x or mean of x is defined as summation x px, where x is a discrete type random variable, x, we have probability distribution x comma px, small x is x1, x2, x3, so on. So therefore, this is the value. Similarly, variance is nothing but how much is the deviation from the mean value. So that is basically summation x minus mu square into px, where px is the corresponding probability mass function. So in combined form, we can write down this value is this expectation of x minus mu square, just in notation. So open this to summation x square plus mu square minus 2x mu px. So this will be summation x square px, summation x square px plus mu square summation px minus 2 mu summation x px. This is nothing but as a notation expected value of x square, as we are denoting this as expected value of x square px, expected value of x square. And this summation is 1 because summation of probabilities is 1. And yeah, Chirag, why you are unmuting? Some question is there?
No, sir, I didn't unmute.
Yeah, you unmute yourself. Na? Okay, so kindly mute yourself. Okay, so this is xpx. This is nothing but expected value of x or mu. So this is expected value of x square, this value, mu square minus 2 mu square. So that means only mu square. Mu square is expected value of x whole square. So this is the variance basically. Okay. So this is the mean. And similarly, when we have continuous type random variable, then we will have integration. Expected value of x will be integration x fx dx in the same fashion as we have for the discrete case. Here we will have for continuous case. And similarly, we will have for variance expected value of x minus mu whole square, which is integration x minus mu square fx dx, which is expected value of x square minus expected value of x whole square. because instead of now px, we have integration x fx dx. So can anyone define how we will define for mixed type mean, mixed type random variable? Here this is continuous type.
Sir,
If you have to,
sir, yes, sir, like for discrete type till discrete type, we can do this summation part, and then for continuous, we can do integration, maybe like that.
yes, yeah. So we will have for mixed type, we will have certain points where probabilities are there and certain range where fx will be there. So we will add x px plus integration x fx dx, where our discrete part is there, where some points will be there corresponding x into px probabilities and summation of that. And for the continuous part, we will do integration x fx dx, where small fx is the pdf. In the same fashion, we will have for variance for x also. Okay, so this is some simple example where we will have the probability mass function -2 0.1 corresponding x and corresponding probabilities is given. -2 into 0.1 and corresponding probability is there. Probability x is equal to -2. When x is equal to -1, probability x is equal to, this is probability x is equal to small x k. So find out the value of k. So because we know that total probability total is 1, total integration, or here in this case total summation is 1. So therefore this is 0.1 plus k plus 0.2 plus k plus 0.3 plus k should be 1. So k is 0.133. So what is the mean? Mean is nothing x into px. So that is -2 into 0.1 plus -1 into k, 0 into 0.2, 1 into k, 2 into 0.3, 3 into k. So that will be 0.799 because k value is given. And now variance of x, we can find out expected value of x square. So what is expected value of x square? This is summation x square px. So that will be 4, 2 minus 2 square, 4 into 0.1 plus -1 square, 1 into k, 0 into 0 square into 0.2 plus 1 square into k into 2 square into 0.3 plus 3 square into k. That means 3.063. Now variance of x is expected value of x square minus expected value of x whole square, that is 2.42. This is the answer. In the same fashion, instead of if we have probability density function, we have to do the integration basically. So for example, in the case of exponential distribution, this is the PDF of exponential distribution. The mean life or average life of electronic devices, integration x fx dx, which is x into lambda e raised to power minus lambda x dx. Okay, so lambda will be outside. Integration 0 to infinity x e raised to power minus lambda x dx, that will be 1 by lambda square, that will be 1 by lambda. So this is the mean life or average life of the electronic device, because in this case the corresponding we will have correspondingly we will have probability density function here. Similarly, we can extend these ideas. For example, we have expected value of x, expected value of x square, expected value of x cube. So that is basically origin moments or rth moment about origin. So that is nothing but summation x square px. Px is the probability mass function. R is 1, 2, 3, so on. Similarly, central moment, if we take about the mean, expected value of x minus mu raised to power r, where r is 1, 2, 3, so on. This will be nothing but summation x minus mu raised to power r px. That is the rth moment or central moment. Similarly, in the case of continuous case, we will have instead of summation integration and correspondingly probability density function will be there in the same fashion. So that is the extension of mean and variance to moments. So this is the origin moments and rth moment about origin. Relationship is easy to find using the binomial expansion. So you can use mu r is expected value of x minus mu raised to power r. So this is the basically rth moment about mean or central moment. Okay, so you can extend this, open this thing, rcj minus mu raised to power j, x raised to power r minus j. Okay, this will be expectation of rcj minus mu raised to power j, x raised to power r minus j. Now, because this is some summation or integration, if I take the, let us say x is discrete type, this will be summation rcj minus mu raised to power j, small x raised to power r minus j into corresponding probability mass function. So this will be summation rcj minus 1 raised to power j, mu raised to power j into summation. This summation I can take inside. Okay, this summation okay, this summation is there here. Okay, so this is summation over j, and the summation over x is there, summation x raised to power r minus j px. So this will be your expected value of x raised to power r minus j. So this is mu dash r minus j. So in this fashion, using binomial expansion, you can find out that this will be expanding this, and this will be summation. This is a expanding expectation. So you will get this value. Okay, take this, interchange this summation over x and j, and take this inside. You will get expected of x raised to power r minus j. So you will get mu dash r minus j. So this is the relationship between them, which can be easily find out using the binomial expansion here. Any question here? Is it okay?
Fine.
Okay. So, okay, so let us stop here. So next time I will start with the moment generating function and try to finish up to the 6 chapters. Okay, and okay. Stop here first.
Hello.